So when we have multiple outliers, and this actually cases non-normality of the distribution. So when there are outliers in our data, then automatically distribution of our observations is not normal. So outliers spoil the normality of the distribution. So in case when the distribution is not normal, we use other ways to measure distance between the curve and the points, different from the sum of squared deviations. And so the general way to describe these ways to measure the distance is the function you see now. So you see that function is very similar to what we have had previously, but instead of square, you see the rho. This rho is not a coefficient, rho is a function. So if rho, for example, rho of u is u squared, then we'll get the OLS. So OLS is is a particular case of this method. So, but for contaminated data, for the data where the normal distribution is spoiled by the outliers, we use different rho functions. And the most popular two are the Huber loss function and the Tukey loss function. You can see the formulas. So the idea is that the Huber loss function, it is like a square for small deviations, and it is like a line for big deviations. So Huber loss function is an attempt to join the least square method and the least absolute value method. And the Tukey loss function is a way to to deal with the outliers in such a way, just to say that if there is a point that is very far from this general cloud of points, of observations, if there is a point that is very far from this cloud, we just move it closer to the cloud. So you see that for big arguments, Tukey loss function is equal to 1. So we just ignore the distance for far points. If a point is very far, we just say that the distance is, let's say that the distance is equal to 1. So, and real distance, actual distance is ignored, actual deviation. So some other functions can also be used as a rho function. So here you see the most popular ones. The first one is actually just a square. So the first graph is a graph of rho of u that is equal to u squared. The second is the Huber function. So you see this is a part of a parabola, and then you see lines. And the Tukey function is also graphed here. So you see that for small arguments it's also kind of a parabola, but for big arguments it's a horizontal line. So it's a constant. So this means ignoring of distance between the curve and the far situated points. And so there are some other functions that can be used for the same purpose. And so there is no answer which one is the best one. You are to compare. In each particular case, you are to compare and just to see which one gives the best result. So what is the digest? The ordinary least squares estimators are easy to calculate, so as they are found by just multiplication of matrices, and this is a very simple mathematical operation. But they are not robust. They are not robust in case of outliers, and so they are optimal only in case of normally distributed errors, and normally distributed errors is almost a synonym of the absence of outliers. M estimators with raw functions of Huber or of Tukey or with some other raw function are difficult to calculate, as we need some numerical methods to find the minimum point. As you can see here, these functions are very complicated. It is not so very easy to find minimum point, so we cannot use standard calculus approach like find partial derivatives and so on, especially for the Tukey loss function. You see the shape of this function is such that we cannot use the standard way to find minimum point, and we need to apply some numerical methods. And for numerical methods, we usually need a start point, and we usually need the OLS estimators to use as a start point, as a 0 point, for some numerical minimizing methods. But, so the advantage is that M estimators are more robust to outliers and then can be used for highly contaminated observations. So for observations with a high proportion of errors, high proportion of outliers. There is another important question, important problem we have not discussed yet. How to find the degree of a polynomial. So I told you that a polynomial is usually used to describe this dependence between x and y, but polynomial of what degree? So there was m there, so how to find m? You see that this picture shows you that it is a bad idea to make m too high, too big. As here you see that, so black points are observations. The black line is a graph of a first degree polynomial, of a line, and this is a good model to describe this relationship. We see that points are pretty close to the line, to the black line. And the blue curve is a polynomial of degree 10. And this is what we call an overfitted model. So from the first point of view, the blue curve is a good curve as the distance, the deviations are zeros. So just there is no deviation between the points and the curve. We say that a good curve is a curve that is close to the points. And this blue curve is absolutely close. So there is no distance. Sum of square deviations is equal to 0. So from the first point of view, it is a good model, but not. Actually, it is not good. It's a bad model. It is overfitted model. Why? It describes our observations perfectly, but it is bad for prediction. So if we use this model to predict y's for some other axes that are not part of our sample, of our observations, then it will show us something absolutely different from real y. So this is overfitting. So how to find optimal degree of a polynomial? So to make it to make this model fitted but not overfitted. So the best way is to start with a line, with a polynomial of the degree 1, and then you increase the degree of the polynomial just by 1, and each time you estimate the coefficients, thetas, and you look at the coefficient at the highest power of x, And you are interested, is this coefficient close to 0 or not? And so if you see that the highest power of x is m, and the coefficient at x power m is close to 0, this means that you don't need actually this power, so that a polynomial of degree m minus 1 is enough, is sufficient to describe what is happening here. So the idea is that you increase the degree of the polynomial just by 1, so starting from the degree 1, 1, 2, 3, 4, 5, and so on, until the coefficient at the highest power of x is close to 0. Close to 0 is something like 0.001. So if you get something like this, you say that you don't need this power. And in practice, usually powers no more than 5 are enough. So degree of a polynomial in the models that we use to predict y in our real life that we use in practice are usually like 1 or 2 or 3 or 4, sometimes 5, but models with a polynomial of the degree higher than 5 are very rare. So this is just for general information. So if it seems to you that, for example, a polynomial of the 11th degree is the best one, this means that this is something strange. So this is some exotic situation. What we have just discussed was a situation when we have two variables, a pair of variables. So that is why this is usually called a paired linear regression. But another model that is also used very often is a multivariate linear regression, when y depends not just on a single scalar x, but when y depends on several independent variables that are usually called explanatory variables. So, and we use a model very similar to the previous one, but so what is multiplied by thetas is not, these are not powers of x, but these are independent x's, x1, x2, x3, and so on. So we have m explanatory variables, we have unknown parameters, thetas, and we have errors. And so the approach is absolutely the same. So I won't repeat what I have already explained you. So we can use m estimators to find coefficients, to estimate thetas, coefficients of the model. So the approach is absolutely the same. So when the errors are normally distributed, the best way is to use OLS, to use rho of u equal to u squared, so to square these vertical deviations. If there are outliers, if the data is not normally distributed, the best way to deal with this situation is to use more complicated draw functions, like Huber and Tukey loss functions. So the one important thing you should mind here that is not actual for the paired linear regression is what they call multicollinearity. So this means that this is the situation when some explanatory variables are highly dependent on each other. So this is a bad situation, and there are special methods to deal with this. Unfortunately, I haven't got enough time to explain this, but please mind this problem, so that sometimes this model is working not as good as you expect because of these multicollinear explanatory variables. So, and there are methods to deal with this. So you have a linear regression model. You have estimated the coefficients, the parameters, thetas, the model is working somehow, it predicts y's for given x's, and how you can understand, is your model good or not? So are these predictions accurate or not so very accurate? So the most popular way to do this, to understand, I mean, how good your model is to calculate what we call determination coefficient. So after all thetas are estimated, let us say that we have a paired regression with a polynomial of this kind. So you can find predictional values of y's. So for each xi, you can substitute xi to the model and calculate yi hat. So yi hat is what your model predicts for the ith observation. And then you can calculate the residues, so differences between what you observed and what your model predicts. So epsilon I hat is called the residue, and this is the difference, so between yi is what you have just observed, and yi hat is what your model predicts, so what your model thinks the y should be in this case. And then you can calculate the determination coefficient. So the formula, it is the standard symbol for the determination coefficient is r squared. And so the r squared is calculated according to this formula. This is sum of squared residues divided by the sum of squared deviations of y's from the y bar, from the sample mean. So the determination coefficient always takes values from 0 to 1, and it shows us how much of the y can be explained by our model, can be explained via x by our model. So, for example, so we know that y partially depends on x and partially depends on something else. And so for what degree we can explain y when we know x? So this is what the determination coefficient tells us. So for example, if r squared is like 0.8, what does it mean? It means that 80% of y can be explained by x, so that x's give us 80% of total information on y. So y can be predicted, can be explained with x only partially, but if r squared is 0.8, this is a great part of y that can be explained with x. So so this means that the more close the determination coefficient is to 1, the better. So if you use a regression model, but the determination coefficient is like 0.2, this means that this model explains y very poorly. So you cannot use this model for any predictions, as so real y will vary, will deviate very much from your prediction. And if the determination coefficient is close to 0, is something like 0.8, 0.9, and so on, so this means that y can be predicted with the help of x to a very high degree, so that the model can be used in practice.